Hello, everyone. This is Keith Bernstein with Future Facilities. Thank you for joining us today. On the call with us today, we have William Villers from Ten Tech and DJ Pandian from Future Facilities. At this time, I'd like to turn it over to William.
Thank you. Want to make sure you can hear me okay?
Yes.
Yes, good, perfect. Okay, so I have a few little slides discussing the subject at hand today, and then we'll pass on to the software side of the house, the Future Facilities. So I represent a company called Ten Tech LLC. We are a women-owned ATR registered small business, and we deal with a lot of military equipment. We deal with a lot of government agency or prime contractors. We have offices in California and in Massachusetts. Practically what we do for our customers is we bring subject matter expertise in the areas of mechanical engineering, analysis, so shock and vibration, and more importantly for today, thermal design and electronics cooling. We are part of a certain number of working group and activities such as GUIDEP and VITA to be part of the decisions and the discussions being done on electronics and particularly on military and embedded systems. Who's speaking today is myself, so I am the Director of Engineering of the company, managing the analysis team and a certain number of programs and projects, and some technical aspects including tool selection and evaluation and benchmarking. I come from the aerospace industry, about 25 years of industry experience in different categories and different industries, mostly military and aerospace, but a fair amount of high-tech electronics as well. Managing or actually performing tasks in the engineering world, mostly mechanical, and again, thermal is a big part of what we do. I'm based in Los Angeles, and this is my picture in black and white and my business card with the contact information. What we do as a company, naturally we do a lot of things outside of thermal, but thermal is a big part of our business. About, I'll say 20% of our business is military electronics. The other main, I guess, topic of activities is shock and vibration, steel and defense electronics. I'd say 90%. If you combine all the things together, naval architecture and defense electronics, they kind of go together based on what we do. About 90% of what we do is related to defense electronics, electronic systems, embedded electronics. So let's look at what we're talking about. I'm sure most of you know what we're going to talk about, but let's review a little bit of the electronic systems we're talking about. And so I have a certain number of systems that are displayed there. They all share the same characteristics. They are packaged electronics. So on the top left, we got the radar system. So this is a little private plane. Still has a certain number of avionics. Okay, you see this little black box there. This is not the flight data recorder. This would be this one, but this is radar processing, image processing, you name it. Towards the right, this is one of the avionics bay for the F-16. So if you think about all those jet fighters, the majority of, and UAVs for instance, the majority of what's inside is electronics. To allow it to fly, to allow it to see things, to allow it to find foes and look where the ground is, follow the ground, and so on and so forth. So basically the installation is a bunch of shelves and a bunch of boxes sitting on the shelves. And one thing you notice, compared to your nice and cool office environment, the air conditioning is not there. So, and by the way, the electronics inside there is a whole lot more powerful, therefore dissipating a lot more heat than your computer in the office. So if we look further at the bottom, we see another part of quote-unquote packaged electronics. This is a control room for, this one is a nuclear-powered aircraft carrier control room. so it controls the nuclear engines there. In the middle, this is the same package electronics, but this time you notice the difference, a lot of dust, a lot of junk on it, and this one is inside a Humvee. So same thing, you got a lot of high power electronics in an environment that has dust, that has heat generated from the outside. This is nowadays, those kind of electronics are seeing a lot of 100C ambient or 100F ambient, and a lot of high temperature requirements. And on the absolute right, this is not the Apple Mac Pro computer. This is actually the guidance system for a Navy missile, and we got a lot of the electronics that are displayed there, and we use the frame of the missile guidance as the cooling system, so as the heatsink. So all those electronics are kind of the same type of electronics packaged slightly differently, but one of the things you notice is there's no room to cool it. So we need to find ways of cooling it. So a typical statement of work, if you wish, of the system, so all the things we have to deal with. So in the military applications, there are two big words that are being used. You can call them buzzwords or not, COTS and SWAP. So COTS means commercial off-the-shelf components. Basically, we want to use as many off-the-shelf components, meaning an Intel Xeon processor, an NVIDIA GPU, memory from Samsung. We want to use as much of those components as possible in military applications. And the logic behind this is a whole lot cheaper than designing your own processor. Now, this comes with the drawback is those hardware are not designed to go at 50,000 feet altitude, or they're not rated for 100F, 120F, none of that, so the manufacturers do not guarantee any of that. So to be able to put together systems using COTS component, you have to be able to predict the performance, because there's nothing in the literature or there's no data sheet that's going to tell you, yes, this is rated for as much as you want to use it. Now the second one, and this is another problem that comes, is swap. So what happens is we want more power, we want to be able to do more stuff with our electronics. And when that doing more stuff means essentially dissipating more heat. You want more compute power, therefore you're going to dissipate a lot more heat. So that will be fine, okay, fine, we need to cool that. But at the same time, we ask you to use less space. So we want smaller and smaller electronics, but we want them to do more and more. And this is particularly true in the UAV side of the defense electronics systems. There's a whole lot less space in a UAV than on an F-16, for instance. The shells are much smaller. Global Hawk is probably the only exception, and even Global Hawk, you have you don't have that much space. And the power densities that we see there from probably 10 years ago, it's easily doubled, easily, probably even tripled. So the space is the same or smaller, and we have to deal with more electronics and more power dissipation. And on top of it, so we have seen that all those, even in a cool down environment, even a favorable environment, there's difficulties to cool that. Now we have increased requirements for the environment, particularly altitude. At sea level, let's turn the air conditioning, let's turn the fans, we can cool everything. Now when you go 40,000 feet, the fan is pretty much dead wood. It's very useless. So there's things that have been done as far as water cooling or liquid cooling, so more jet fuel, using the jet fuel circuit to cool down things. So there's a lot of things that need to happen, need to be made for this electronics to actually survive its environment. And all of this needs to be looked at a prototype level before we actually, especially this is military equipment, so a failure on the field is not exactly like you dropping your cell phone on the at home. This is the jet fighter loses its radar system. So that's a little more dramatic. So we want to avoid failure as much as possible. We want to be able to predict it, and we want to be able to create good designs that work well the first time. So today we're going to look at particular details of putting together thermal models and doing thermal analysis for what's called an ATR system, so air transport rack. This is airborne system, so the ones that we saw on the F-16 shelf, so this is exactly that. Basically, this is a big heatsink, external heatsink, so it's an aluminum box that has to have a certain shape and form. We can't just decide to make it whatever we want. The avionics bay or the radar, all the bays have a particular space and volume for you to occupy, and you can deviate from that. So the industry in general has devised a certain amount of standards and is working with ATR chassis, for instance. So the outside is an aluminum heatsink that is designed to conduct the heat away from the payloads. The payloads are the cards inside. So if we look at the picture in the middle, a payload is essentially a board. So it's a little more than a PCB. It's actually a full-blown single-board computer. So if you look at the on the right side, this is the equivalent of your workstation in the office is packaged in something that looks like a card, like a PCB. So there's a PCB, but there's also a GPU, there's also a CPU, sometimes two CPUs, sometimes 16, 32 gig of RAM or more. And all those payloads are stuck inside this chassis and conduct some of the heat or most of the heat away from them towards the walls outside of the chassis. And some of the tools that are used for that, so you see the wedge locks in the bottom, so those are little aluminum mechanisms that are there to connect the payload's walls to the payloads to the walls of the chassis. So this is conduction cooling. The payloads themselves are connected to a backplane, so this is the main board, if you want, that is in charge of distributing all the instructions to all the computers on all the single board computers in the system. So conduction cooling is one thing. Now again, this has worked for the most part previously. Now as we're increasing the power density, we need to be a little more clever. We need to add stuff like fan cooling and again the liquid cooling. So there's a lot more that goes into it. So the systems turn from a simple aluminum box into a more intricate system where you have a couple of liquid loops, you have airflow that needs to be looked at and that needs to be passed to the proper payloads. Same thing, the payloads are not all the same. So there's different types of single board computers or that perform different activities that have different mission or turn on and off at different times during the mission. So this also you need to be able to look at, okay, are we actually clogging all the high power density cards together and creating a hotspot or not. So you need to be able to juggle with all that. So this is what some of the things we were going to look at. Before we start this, I wanted to kind of put out why we're using this tool and why we believe in it so much. And the main reason I say is that it gives us a quick and accurate thermal simulation. So we are systematically within a few degrees of test when we do test. We're capable of dealing with very large models, and I mean, I'm sure if you guys work in this kind of systems, you know those assemblies are enormous. A single board computer has hundreds of parts or thousands of parts. There's sometimes 10, 12 of those in a chassis. one of the things we like is the COTS functionality as well. There's reusable libraries and catalogs. So we do our own COTS inside our thermal models. The prime contractors do COTS for their design, so why not us? Okay, we can reuse a single board computer from another system. We can reuse, so we have all those things. Quite often we work at different levels. We start with a simplified abstraction of the model, a bunch of boxes together dissipating heat. This has helped us a lot in RFP, for instance. Is the thermal design we're proposing even going to work? So later on, when we refine the model, and that happens at the board level, the component level, at any level, we can turn a little block component into a fully detailed BGA model, for instance, with all the balls, with all the solders, with everything. And at the same time, we need to be able to accurately model the environment. The altitude, for instance, is a very, very important thing. All fans are, not necessarily as capable at higher altitude. We need to be able to look at that. We need to have things like, well, what if we have radiation coming from the outside, or we need to look at all this stuff. And equally importantly, we need to be able to do that fast. And so this is one of the things that we like a lot. Is naturally this is CFD thermal code, so this works well in a distributed memory environment, so we can distribute the models across processors. And equally importantly, you can also do that at a cloud level. So using a company like Rescale, Six Sigma AT actually does work in a high-performance computing environment cluster, and including cloud-based. So those are some of the things that I wanted to point out that we like, and I'm sure I'm going to pass the reins to my colleague there, and I'm sure he's going to show you some of that and even more. Back to you, back to the studios.
Thanks, William. Hello, everyone. This is Vijay Pandian. I'm an applications engineer with Future Facilities. I've been with the company for the last almost 4 years now. And my background is mechanical. I have a master's in mechanical degree as well. So William kind of explained a little bit about the software and the problem statement as well. I just want to quickly give a brief introduction about the company Future Facilities, and for the people who do not know about us. So Future Facility is a CFD thermal solutions company, and we provide thermal solutions specifically for electronics cooling and all the way up to data center modeling. And Future Facilities developers were the original developers of Flowtherm back in the Flowmatics days. And they moved on to create the product Six Sigma AT now. And the product Six Sigma AT is being used by several customers like around the world, like Cisco, Tails, Facebook, and etc. And we solve for conduction, convection, and radiation, conjugate heat transfer. And we use our own proprietary solver, which is a Cartesian-based gridding, and we've developed a new gridding called multi-level unstructured staggered grid, MLUS in short. We've been working on that for the last 3 years, and we released it a few months back. So that's a quick introduction about Future Facilities in Six Sigma ET. So I want to quickly dive into the software and show you what can be done, and how the problem statements William mentioned can be addressed using the software. So with Six Sigma AT, when we got down to the drawing board and when we wanted to create a new software for electronics cooling, we thought as engineers we wanted to create a tool that we would like to use ourselves. So we want a clean interface, intuitive interface, and for new users it should be easier to find things. For experienced users, they should concentrate more on the design process rather than fighting the tool. And the electronics cooling industry has been growing, and the power industry has been growing along the years, and this gives more puts more burden on the engineers to meet the specs at the same time satisfy the power and increasing power densities as well. And especially in avionics and military industries where the standards are pretty stringent, it adds additional burden on the user as well. Apart from that, not many people realize that they have to fight the current CFD tools what they're using to get the results what they need, which is expensive in terms of time because you are the expensive resource in your company. So let's look at this example. I have I have a small solution domain, and I'm going to bring in a CAD file because normally all these models are already available in a CAD package. It's designed by a mechanical engineer. So instead of recreating it just for thermal, I'm just going to use the CAD file and modify it to suit the tool. So here I'm going to bring in the CAD file payload. And this is importing. I'm going to change the units quickly, so it's in the right units. And you can see it's a payload chassis here. And let's quickly move that into the domain by aligning it. Okay, slightly bigger, but it's fine. You can quickly snap to it, so you don't have to go and key in the values manually. So here I have a payload chassis, and you can see there's a top cover and a bottom cover. Let me quickly hide that so we can see what's inside in the payload. So here I can see a board with housing a few components in there, and connectors and a lat lid lock. So using CAD, the only problem is you do not have intelligence to those solids. You cannot add trace informations or change the or add a heat spreader into the solid because they are a dumb solid. They do not have any intelligence to that. So by using the converter feature in ET, you can quickly select a solid and change it into a PCB. So here you can see it moved from the solid repository to an intelligent object called PCB. And you can also notice that it is retaining the shape, holes of the PCB from the CAD file as well. So, and another thing is the holes are categorized as a separate object within the PCB. So if you think that the holes, you don't actually need to model the holes, you can either delete it or uninstall it from the board. So that's an easy way of saving grid by not modeling the holes. So now I have the PCB ready. Normally when you're in the design stage, you do not have complete information about the board. So here you only know it has got a 10-layer board. About each layer is about 80% copper, and you sit and calculate the normal and plane conductivity and key into that. But using the native object, what you can provide all the information in the property sheet, and the software will calculate an effective normal and plane conductivity for you. And later on, when you get the designs from your electrical engineers, you can switch the different levels of modeling on the board, and you can go from a simplified model all the way to importing trace into the PCB. For now, I'm just going to stick with simplified modeling. So here I've provided the layer properties. So next step is bringing the components in. Again, the components are also modeled as dumb blocks. There's no material attached to it or any other properties. So I'm just quickly going to do a rubber band select and use the convert to options, which I used earlier to change the PCB. Now I'm going to change that as components. So when I convert them as components, you can see it moved it up the order, and it also attaches to the closest board available to those components. And you can see everything is attached to the board. And by doing this, it establishes a parent and child relationship. So once you have this relationship, if you want to move the geometry to a different location, for example, I want to move this by, say, 5 millimeters, I can just select the board and do it. Everything on the board moves along with that. So parent and child helps you fast track, changing geometries, and also at the same time avoids any error that can happen when you're trying to move multiple objects. So let's bring it back to the original locations. And you can either assign power manually, or you can use a CSV import to bring, add powers to this components here as well. So let's add 10 watts randomly to those 3 components. So here I have a bunch of connectors, and I can see they're modeled with really great detail with the sockets and everything. These are not thermally significant, but and normally in other codes you have to sit and change that shape into a simple cuboid, or do some sort of simplification process which involves you spending time on it. Rather, in ET, you can select those objects which you think are not thermally significant. They may either act as a placeholder or just a resistance to airflow. You can select the modeling level to approximate. So by just changing the modeling level, the software knows that it does not need to spend more grid or add more grid to capture that particular object. It will just use the grid that's being generated by other objects and try to capture the shape of these selected objects and model it approximately. So a few clicks, it will fast track your grid generation process and also save grid as well. So that's done. And I'll also do the same thing with the latches. So change that quickly to approximate, and let's add probably a material which would be ABS or polycarbonate to it. So I have a quick model ready, and when you are modeling something like this, you want to keep track of the weight it measures. So if you click on the chassis, you get a construction detail where you can constantly track what's the weight of the payload after you've added or made some changes to the model. And you can also click on the room summary, chassis summary, where it gives you an overall idea of what's the total power value of that particular chassis, and what's the component power values and everything here. So I have the model ready. So the next step is generating grid. So let's quickly uninstall that by to create an an open environment. And so grid generation in AT is automatic. So since the objects are self-aware, they know what they are. The software recognizes that, and every object has its own grid rules. For example, if you take a board, you want to create, you want to add inflation layers above and below the board to capture the boundary layer. If you have a heat sink, you would probably add 3 or 4 grid cells in between the fin spacings, and probably a grid cell for the thickness of the heat sink for the fins to capture the physics around it accurately. All those things are done automatically by the software. So if I hit show grid, so you can see that's the grid being generated, and that's the grid on the extreme faces of the model. But as I move the grid plane closer to a component, you can see the grid is defined only where the objects are, and you can see there's an inflation layer right above the PCB as well as the component. So as I keep moving away from that, you can see the object, the grid refines automatically. So having an automatic grid generation, object-based grid generation is really helpful, because you don't have to repeat the process of grid generation again, or change the process of grid generation again and again. You just hit generate grid, the software will automatically update the grid based on the new location of the object. So now we have the model ready, grid generation is done, it looks good, and now the next step is to solve the model. So here I have a model which is already been solved. So if you look at that, sorry about that. Here I have the payload already solved. You can see the top cover, and I can hide that. So here I'm just going to plot the the power, so you can quickly look at what the power values are, and look at the temperatures here, and you can see the temperature is about 200 degrees C. Again, the temperatures are exaggerated just to show you the difference in plots. So here I know that the design is okay for the condition. Now what I can do is I'm going to reuse this particular design in a bigger rack, the ATR chassis now. So the software allows you to select the chassis and add it to a library or a favorites. So here I have a couple of payloads added in my favorites library, and I'm going to reuse this in a bigger chassis. So here let's look at the ATR chassis. Sorry about that. So here I have the chassis already imported using the same import process, and I've added materials, and I've added the top cover just to show you what's inside the model. So similar way I know that similar way I did the convert to feature in the previous payload model, I'm going to do the same thing here just to show you that's the back plate here, and I can also convert those objects as components quickly. And I've got a back plate now. I'm just going to assign probably 2 watts each. Now you can see the slots here, back plate and the chassis. Now I'm going to bring in the chassis, but before that I'm going to use something called the chassis bay. So all these chassis are mounted in a shelf kind of a setup in the actual model, and we have similar objects in the software to help you quickly build them rather than creating a shelf with a bunch of solids by yourself. So here is a payload chassis. So I'm just going to bring it and drop it into the model, so you can see that it's a shelf model, and so it's a shelf with about 7 slots, and this is completely parametric. You can change it to be 7 slots, 5 slots, and and you can also change the direction from right to left or top to bottom, and the shelf is parametrically changed. So let's go back to the original shape. So that's the chassis. Now let's quickly bring the chassis into the domain. I'm arbitrarily placing it to match the location here, and at the same time on the right side we're going to move it up a little bit. Yeah. So once you have the chassis in the chassis bay in the right location, all you have to do is select the payload, drag and drop it into the bay. So this way, if you have multiple payloads, you can drag and drop different payloads, play around with the design, and see which arrangement satisfies the requirements and meets your design goals. So here I have one. You can drop another one as well, and as I'm dropping it, you can see it's adding it to the shelf. So now I can go back to the original chassis, the bigger one, and I can click on the summary to look at what's happening. So here you can see it's adding about 563 watts because of all the 3 payloads I've added. And again, you can look at the property sheet, which gives you an idea of what the chassis weighs when you add 3 payloads to the model. So that's done. So I've added the source to the chassis, materials is added. The next step is adding fans to it. Here again, the fans being brought in from the CAD. I'm just going to select them quickly. Sorry. And convert them as Six Sigma native objects, so I can go in and add a fan curve to it. So I'll just quickly change that to curve and add a fan curve. So fan curves can be imported through a CSV file, so you don't have to enter them manually. And I'm going to quickly change the units here, and that's done. So you have the fans added, the source payload in place, and the model is pretty good, is almost ready to be solved. So the next step is when you are building chassis for avionics and military applications, altitude scaling is always an important thing. Usually users manually derate the fan curve for densities and input the new curve in. But in ET, you can just set the location and the altitude in the software. For example, here I would want to set it at about 35,000 feet. And you can also provide latitude and longitude. This will be used later if you have solar radiation. So the software will give you a set of intensities calculated based on your interval and longitude and latitude, cloudness, and you can choose the highest intensity and apply it to the model. So here I'm just going to just set the altitude. And once the altitude is set, under the air properties, you have an option to scale the densities based on altitude. And we just not only scale it based on altitude, we also scale it based on temperature as well. So in this case, I'm going to scale it based on 75 degree F. That's done. Now you can select the fans here. And under fan curve, you also have an option to say adjust for density. So when the model is solved, you can actually see the derated fan curve at that particular altitude for that density. So the model is almost good to go, and you just have to hit generate grid and solve the model. So here I have a model already solved, and let's quickly hide the chassis so you can see what's inside. So the first step is let's check the fans. The fans have been derated for 35K feet. Again, you can see that. And if we look at the results in the fan curve, you can see that's the actual fan curve being inputted. And that's the derated fan curve based on density. And it does it for all the fans. So, and the next step is let's quickly look at if any component is not meeting the spec. For example, in this case, I want all the components to be under 100 degrees C. So you can quickly check that using the pre-configured plots. So the software knows it has to hide anything that's obstructing the view of components. So it pretty much hit the top cover and the bottom cover, and it's just showing me the mean component temperatures. And if, especially dealing with complicated model like these, you want to just look at one particular chassis in its own view, you can do that too. Just double click on any chassis, and it opens up that in a like a browser tab view. So now you can just look at the change the views, look at the results of that particular chassis in its own view. So here I'm going to change it to say mean surface temperature. You can see it's plotting the mean surface temperature of that particular slot. And the same thing with component temperatures as well. It's always good to look at the plots, but it is better if you have what temperatures they are. So I'm just going to plot them here. So you can see it's annotating everything, all the mean component temperatures in that particular board. So using the pre-process, the post-processing tools, pre-configured plots, the automatic grid generation, you can quickly accelerate your thermal cycle, design cycle, by avoiding errors and quickly checking if your designs have have a significant impact on the results. You can also use, for example, here I have two payloads with one at 35,000 feet, another one at sea level. You can use our compare model tool to look at two different designs in the same view, which gives you a better understanding of what's happening in the model. For example, here I'm going to plot the mean component temperatures of both the boats. As you can see, the sea level one is much lower than the the model at 35,000 feet and 75 degree F. So this gives you a clear picture of how that particular design change has affected your thermal modeling as well. So that's about the ATR chassis, and I want to quickly touch a little bit on liquid cooling and a little more on adding grid, or how do you refine grid as well. So for that, I'm just going to use this cold plate example. So you can see there's a duct, and a supply duct and a return duct, and here's the cold plate here, the bottom one, and that's got some fins, and the top cold plate, if you see, it's got the cavity for letting the air, the water flow in. So in AT, liquid cooling is possible, and it's very simple to set up. And using the cooling duct tool, you can create ducts quickly. Even complicated ducts can be created. You don't have to necessarily bring it from CAD, which is useful, but it just takes hit on the grid. So here I have the model, and let's look at the grid that's been generated by default by software. So let's quickly look at that. Let's make it wireframe, and let's see the grid. So that's the grid on the cavity right underneath the right above the component. So you can see that it's adding grid to the fins and the cavity region, but I'm not happy with the amount of grid that's being generated here. So you can add grid controls to those objects. Here I've added a geometry-based grid control. So geometry-based grid control is a quick feature to add grid to a specific part of the object, for example, the solid part or the fluid part. So in this case, I'm going to add just to the fluid part. So that's what I've set here, and the maximum cell size is about 0.5. So when you hit generate grid, you can see it's going to refine the grid only in the fluid region. So if I make the chassis transparent, you can see it's only adding it in the fluid region. So another example would be is, let's say you have a perforated plate with probably square holes, and you want to model it in detail to capture the pressure drop across it. But the problem is when you add grids to each hole, it is a very tedious process. By using geometry-based grid control with just a couple of clicks, the software automatically adds grid where you need it, whether the fluid or the solid section. So again, there are a lot more grid controls, but I just wanted to highlight this one in particular. So I have the grid generated, everything is added. I am satisfied with the grid. So then you can run the simulation, and here I'm just going to quickly show you the fluid path, flow path. So here you can see the cold fluid entering the cold plate, and as it passes through the fins, it carries heat away, and you can see the warmer fluid leaving the system as well. Yep. So that's a little bit about liquid cooling, and we also have an option to run transient as well. For example, in the bigger ATR chassis, sorry about that, you can select transient, and you can fail a fan here. For example, in this case, I want to change the status from on to off, and you can set the time steps and run the simulation, and you can either start it from scratch, or you can run it from an already simulated steady state as well. So you get a clear picture of how long it's going to take for the system to overheat or go out of spec when that particular fan is turned off. So those are the highlights we wanted to show today. If you have any questions, please let us know. Keep.
All right, going over the chat feature, there were a few questions that came in. First, what EDA file formats does the software support?
Okay, so under Import tab, you can find the different file formats we support, which also includes MCAD and ECAD. With respect to ECAD, it is IDF, IDX, XFL, and for trace information, we allow you to import Gerber file formats.
Another question that came in, can you model heat pipes?
Yes, we can model heat pipes, but similar to other softwares, we only model it with a high K value. But the good thing about heat pipes in ET is when you have a heat sink and you attach a heat pipe, it becomes a child of it. So you don't have to necessarily move the heat pipe along with the heatsink. Just move the heatsink, heat pipes move along with that, and it's much more easier. And we also allow you an option to use a cat shape if it is a really intricate, complicated heat pipe design.
Another question that came in, how many grid cells is that model, and how long does it take to solve?
Okay, so let's go back to the ATR chassis. So this is about, sorry about that. I think I closed the model. Sorry about that. So the model was about 39 million grid cells, and I solved it on 7 cores, and it took about 2 hours to solve approximately on a 7-core machine with 128 GB RAM. So it takes about 6 to 7 GB of RAM to solve it.
Is it possible to use input temperature-dependent power in a model?
Yes, you can have temperature-dependent power, especially when you're running models with higher temperatures. You're always worried about the leakage currents. Yeah, we do have an option. It is you just have to go in and turn it on from the in the solid objects here, and there's an option to check allow temperature-dependent power. Then you select a component, and you have an option to specify that.
Can you model phase change material?
Yes, we model phase change by providing a temperature-dependent specific heat. We do not actually model the change in phase, but we kind of fake the specific heat to simulate the phase change here. And it can be you can select a material, and when you have transients on under specific heat, you have an option to set it as temperature dependent, and you can specify the specific heat curve as an input for phase change.
Another question that came in, can you do optimization?
Okay, so optimization can be done in ET, but it's a bit of a manual process. We do not have an automatic feature. So we call it as fact study, which stands for parameterize, analyze, and compare. Using that option, you can set up different variations of design. For example, you can run a model with 10 fins and a heatsink, change the base thickness, and then you can find the optimum solution that works for you.
Thank you to everybody for taking the time out of your day to join us, and thank you, William and DJ, for the presentation. Have a great day.